Okay, so let's get started with today's activity. So this time we're now doing mass mole conversions involving compounds. So a classic example of this. So previously we did mass mole conversions involving a sample of an element. This time we are dealing with a compound. So what I want us all to start off on is to determine the mass in grams of a 3.2 mole sample of calcium phosphate. So just as a refresher from last time, so if we're starting from moles, and we want to go from moles to grams, what principal conversion factor are we using? What's our conversion factor that gets us from moles to grams? Molar mass, exactly. So what I want you all to do to start us off on today is to complete this conversion and tell me what is the mass of this 3.2 mole sample of calcium phosphate.
No, I think there's the straw in there.
Yes.
Is that the mass that we did in the formula?
Yep, exactly.
Okay.
I think
So we don't have to calculate.
Yeah.
Okay.
oh,
Yep.
Wait, is that calcium? Or, I mean, CH3?
It's just calcium. The number of calciums is implied by the formula name.
Yeah, but what is the?
There are 3 calciums.
Okay, so it's CH3.
Yeah.
That's what I was asking.
Everything go.
yeah, I forgot.
So I hope this first example started to get everyone in the rhythm. So let's now talk a little bit about how we'd solve this problem. So we're going from moles to grams. So we're going to use the molar mass or molecular weight as our conversion factor. We know that we have 3.2 moles of calcium phosphate. And we also are given the molar mass. So this 310, what are the units of molar mass given typically? What are the units of molar mass? Gram per mole, right? So we know that there are 310.1767 grams of calcium phosphate per every 1 mole of calcium phosphate. And if we punch that into our calculator, let me break out the calculator for that. So if we punch that into the calculator, let me switch to one that's working. So we have 3.2 times 310.1767, and that in turn gives us 990 grams. Now, why did I round my answer? Let me zoom this down. Yes, exactly right. So the reason why this answer has been rounded to 990 is because our input has how many sig figs? 2. So how many sig figs should our output have? 2. Exactly. So let's now continue on and let's talk about another way that we can utilize Avogadro's number to do more complicated unit conversions. So Avogadro's number allows us to convert from moles to atoms for atomic species. So we know that a mole of atoms is 6.02 times 10 to the 23rd atoms. So to showcase how this will pan out practically, if I said I have 1 mole of carbon atoms, that would correspond to 6.02 times 10 to the 23rd carbon atoms. Okay, so depending on what species you're referring to, depending on what element you're referring to, you'll change your label to specify the given element. So in this case, we're talking about carbon atoms. Okay, additionally, Avogadro's number allows us to convert from moles to molecules or formula units if we're dealing with a molecular species. So for example, a mole of molecules is 6.02 times 10 to the 23rd molecules, just like a mole of formula units is 6.02 times 10 to the 23rd formula units. So for example, if I said I have 1 mole of water, this mole of water corresponds to how many water molecules? Yeah, 6.02 times 10 to the 23rd. But to be very clear, it's 6.02 times 10 to the 23rd water molecules. It's important that you're meticulous with your labels for your units, so that way you do not mix up and perform an incorrect unit conversion. Always write out the full label. Atoms of what? Moles of what? This will save you a lot of grief later on in the class. So to really drive this point home, let's now do an example. So in this case, we're asked to calculate the formula units of sodium carbonate in 1.29 moles of sodium carbonate. So looking at our unit conversion diagram, what units are we starting from? Moles, okay? So we're starting from moles of sodium carbonate. And in the end, we want to go from moles of sodium carbonate to what final units? Formula units, exactly. Okay, now to go from moles to formula units, we use what conversion factor? Yeah, Avogadro's number, exactly. So then, if we have 1.29 moles of sodium carbonate, how many formula units? So how many formula units do we have in a mole? How many formula units are present in 1 mole of sodium carbonate? Yep, exactly. Avogadro's number, which is 6.02 times 10 to the 23rd. And all we have to do now is punch this into our calculator. So we have 1.29 times 6.02 EE23. And that should give us a very large number of about 7.76 times 10 to the 23rd. Does that match what you observe on your own calculator? Okay. So let's write that down. So we get 7.765 times 10 to the 23rd. But let's now round this number to the proper number of significant figures. So looking at this number, how many sig figs does our input have? So how many sig figs should our output have? 3. So we look at our third significant digit. We look to the right. Do we round up or down if we have a 5? Up. Okay, so that in turn gives us 7.77 times 10 to the 23rd formula units. And let's be really clear here. Formula units of what? Sodium carbonate, exactly. If you include your labels, You will save yourself a lot of grief in this chapter. The more clear you are at labeling the units, the less chance you will mix up your units and use the incorrect conversion factor. So what I want us now to do is to work on some problem solving in groups. And I'd like you to tackle the following two brands of questions. I'd like you to tell me how many atoms of iron are in 33 grams of iron and how many molecules of mercury oxide are in 200 grams of mercury oxide. So to showcase how we do this two-step conversion, I'll showcase the first example, you'll do the second. So in the first example, what are we given in the problem? What are we starting from? Grams. Okay, so we have 33.0 grams of iron, and our eventual goal is to report the atoms of iron. What is our stepping stone? How do we access atoms? From what unit? Moles, right? So we're going to need to go to moles of iron. So grams to moles to atoms. And as we talked about last session, let's now highlight the step-by-step process and what conversion factors we are going to use. So to go from grams to moles, what conversion factor do we use? Molar mass, okay? And if we check our reference, we know that we're going to want to divide by our molar mass to go from gram to moles. Now, if we want to go from moles to atoms, what conversion factor do we use? Avogadro's number. And as we've seen from previous examples, we're going to want to multiply by Avogadro's number. So now that we have a general problem-solving diagram outlined, let's now complete this unit conversion and execute on our plan. So we have 33.0 grams of iron. And my question to all of you is, if we're going from grams to moles, what ends up on top? What units are going to be on top? Moles. So in 1 mole of iron, we have how many grams? Where do we get that information? Periodic table. So if we go to the periodic table and we zoom in on iron, I've already have it circled since we dealt with iron previously. What is the molar mass about if you look in your own periodic table? Yep, 55.85. Okay. Okay, so we have 55.85 grams of iron in a mole of iron. Now, if we're going from moles to atoms, what units need to be on top? Atoms, okay? So my question to all of you is, how many atoms of iron are present in 1 mole of iron? Yep, Avogadro's number, 6.02 times 10 to the 23rd. Okay, so we've successfully gone from grams to moles to atoms. Now all we have to do is plug it into our calculator. And can everyone see the key presses okay on the calculator up front? Okay, so we're going to take 33.0 divided by 55.85. And then finally times Avogadro's number, which is 6.02 EE23. And if you push the equal sign, you'll end up with quite a large number. There's a large number of atoms in masses that we can measure on a scale. So let's transcribe that number now. We would get 3.557 times 10 to the 23rd. Now, before we write out our final answer, looking at our input, how many sig figs does our input have? 3. So how many sig figs should our output have? 3. So we look at the third significant digit. We look to the right. Yes. That's Avogadro's number. So it's a general constant that describes the atoms or molecules of a given species in a mole. Think of it like a dozen. So looking to the right, we're going to round up to 3.56 times 10 to the 23rd iron atoms. Okay, so with this problem-solving manifold as a guideline, what I want you now to do is to tell me how many molecules of mercury oxide are in 200 grams of mercury 2 oxide, to be perfectly exact with the name. Okay, and I'll walk around and check to see how everyone's doing. Yes. Yes. Unfortunately, the spare one I have isn't functioning. I don't have one. I'm sorry. Everything going okay? Looks like you're on the right track so far. Everything going okay? Okay. Everything going okay? What are these two separate units?
Oh, this is just like the solution.
Yep. So we're going from grams to moles to mole. The moles is an intermediate stepping stone.
Oh, so
and then go to mole.
Okay.
Yeah.
Thank you.
Everything going okay? Yep, that's good. Everything going okay? Yep, looks good. Okay, looks good. Yeah, everything
So I
going
just picked it up my
Yeah, looks good. Everything going
might get a different.
So I saw a lot of reasonable solutions. So the only thing that's new in this next example is let's first establish the baseline facts. What are we given? Yep, we're given that we have 200 grams of mercury 2 oxide. And in the end, we want to report the molecules of mercury oxide. Mercury 2 oxide to be exact. So what intermediate unit will we go through? Moles, exactly. And more specifically, moles of mercury 2 oxide. Okay, now we know that we're going to need to go from grams to moles. What conversion factor will we use? Molar mass, right? Whoops. That's the wrong pen. We're going to need to use our molar mass, and we're going to have to divide by our molar mass. To go from moles to molecules, what conversion factor will we use? Moles to molecules. Avogadro's number. And we're going to multiply by Avogadro's number. Think of it as going from moles to particles. Avogadro's number is a tool to count and describe large numbers of particles. Okay, with this solution map in mind, let's talk first about how we're going to get this molar mass, the molecular weight. So looking at mercury 2 oxide, can we calculate the molar mass by adding up the mass of each component element? Yep. So what is the mass of mercury? About 200. 200 point what? If we look at our period, 200.6. 200 point what?
200.56.
Okay. We'll round to 200.6. Okay. And now, what is the mass of oxygen? Yeah, about 16. So if we add these two masses together, we get 216.6 grams in every 1 mole of mercury 2 oxide. Does that make sense where we got our molar mass conversion factor from? We added up the mass of each of these two elements found in the periodic table. Now, what we're going to do next is we're going to execute on this conversion. So starting with 200 grams of mercury 2 oxide, if we're going from grams to moles, what units are on top? Moles. So we have 1 mole of mercury oxide per how many grams? How many grams? What's our molar mass? 216.6. Okay. Now, if we're going from moles to molecules, what units are going to be on top? Molecules, right? So then, my question to all of you is, how many molecules of mercury 2 oxide are present in 1 mole of mercury 2 oxide? Yeah, Avogadro's number, which is 6.02 times 10 to the 23rd. Wonderful. Now, all we have to do is enter this into the calculator and we're done. So let's do just that. So we take 200 divided by 216.6. And we get a number close to 0.923. We then multiply by 6.02 times 10 to the 23rd. And that in turn gives us a very large number that we'll write the entire number down before we round. Okay, so let's do just that. So we get 5.558 times 10 to the 23rd. Now I'm not going to put my units yet because I'm going to round this number before I report my final answer. So looking at our input, how many sig figs does our input have? 1. So then, if we round to 1 sig fig, we look to the right and we see a 5. Does that tell us to round up or down? Up. So that in turn gives us 6 times 10 to the 23rd molecules of mercury 2 oxide. And don't forget your labels. Just saying molecules is a meaningless statement. Molecules of what? Does that make sense? Okay. So, any questions on these 2-step conversions before we add another conversion factor to our list of tools? Okay, so let's keep going then. So, just to really drive home this idea, what I want us to do now is I want you now to take a look and practice on 2 more examples where you're going from grams to particles. So in the first case, we're looking at sodium carbonate. In the second case, we're looking at potassium sulfite. So I want you to tell me the formula units found in each of these 2 samples, given the mass in grams. So I want to make sure you're comfortable calculating molar masses and using them in calculation. Any questions? No, but I recommend showing the work just in case you calculate. Sure, you can. But the more work you show, the easier it is for you to check your work and buy you home. And it's right here. So it's very close, but we're starting with grams, right? And this conversion factor only goes to the moles, right? So how do we go from grams to moles? Yeah. What conversion factor do you use? Mhm. So to go from grams to moles in all our previous examples, we use the molar mass. Oh, this should be good. Yeah. And the molar mass is the combined mass of all atoms found in the element. Yeah, next to. So you're very close. This is part of the complete using one more number. Everything going on?
They meant to like a period set up for some use.
Yeah, it's a period.
Oh, I don't have to. One of us.
Everything going okay?
Yeah.
Yep, setups look good. Setups look good. Yes, exactly. Oh, I would just check your calculation for the molar mass, but otherwise it looks good. So let's now talk through these examples. I want you to get in the habit of being able to solve these problems efficiently in terms of pacing. So looking at this top example, we are given that we have 5.5 grams of sodium carbonate. And in the end, we want to report the formula units. My question to all of you is, what intermediate unit are we going through? Moles. Okay. Now, with that established, this is moles of sodium carbonate. Starting with this first gram to mole conversion, what conversion factor will we use? Molar mass. So if we want to calculate the molar mass or molecular weight of sodium carbonate, all we have to do is add up the total mass of each atom of each element. So to do that, let's start from left to right. So starting off with sodium, what is sodium's molar mass from, or atomic mass from the periodic table? Yep. So we're going to round that to about 23.0 grams. And a key thing to keep in mind when calculating molar mass, how many atoms of sodium do we have? 2. So we need to multiply by 2. Okay, is everyone comfortable where we got the number 23 from? Yes. Not in this case. And just as a side note, the reason why I can round to this precision is due to the fact that my initial measurement is of a lower precision. So in general, as long as your molar masses are more precise than your measurements, your answer will not experience significant drift. If I were writing this longhand, I'd write out the full atomic mass, but due to space, I'm rounding just so we can clearly see how we got the molar mass via addition. Yes.
So we don't use 22.99.
It'll give you the same result.
Because I use 22.99.
Yep, and that will work perfectly fine. Mm-hmm. So looking at the next atom, next element in our molecule, what's the next element? Carbon. And what's the mass of carbon about? 12. Yep. So for carbon, we have a mass of about 12.0 gram per mole. Finally, for oxygen, what is oxygen's atomic mass? 16. So we have 16.0 grams. And how many oxygen atoms do we have? 3. So if we add this up using our calculator, 23 times 2 plus 12 plus 16 times 3, we get a molar mass of 106. So we have 106 grams per every 1 mole of sodium carbonate. Okay, so with our molar mass calculated and established, we're now able to execute on this unit conversion. So starting off with our 5.5 grams of sodium carbonate, if we're going from grams to moles, what units go on top? Moles. So then in 1 mole of sodium carbonate, we have how many grams? 106. We just calculated that. Now, as our typical ender for these calculations, if we're going from moles to formula units, what conversion factor do we use? Avogadro's number, which is 6.02 times 10 to the 23rd formula units per 1 mole of sodium carbonate. And if we punch this into our calculator, let's try to get in the habit of rounding, just looking at our calculator output. So we have 5.5 divided by 106. We get a relatively small number. Then we multiply by 6.02 times 10 to the 23rd. So looking at our output of 3.12 times 10 to the 22nd, if we're rounding this to 2 sig figs, what would we write? 3.1, exactly. So I really want you to get in the habit of quickly rounding just from your calculator output. So this is 3.1 times 10 to the 22nd formula units of sodium carbonate, Na2CO3. Labels are important. They help you organize your thoughts and they keep you from mixing up what unit conversion factor to use. Does that make sense to everyone? Okay. Now let's look, and for this next example, I was wondering if someone could volunteer their solution for this problem, and then we'll talk through it together as a class. Yes. Okay. So let's talk through the logic behind this. Just like before, we are given our grams of potassium sulfite, and we're asked to convert to formula units. As always, what is our stepping stone between grams and formula units? Moles. Okay. With that established, we're now going to calculate the molar mass or molecular weight of potassium sulfite. Now, we know the atomic mass of potassium. So if you look in your periodic table, would you please be able to tell me the atomic mass of potassium? 39. Yep, about 39.1. And how many potassium atoms do we have? 2. To help us along, sulfur is about 32.0 grams. And oxygen, we've already seen, is 16.0 grams. And how many oxygens do we have in potassium sulfite? 3. So then, that gives us a final molar mass for potassium sulfite, if we punch that into our calculator, of 39 times 2 plus 32 plus 16 times 3, which gives us a molar mass of 158. You want to get good at calculating your molar masses quickly. That saves you time on the exam. So we have 158 grams per 1 mole of potassium sulfite. Now I have all the information I need to execute on the solution for this problem. So let's mix things up and use a different pen color just for variety. So we have 20.3 grams of potassium sulfite. If we're going from grams to moles, as always, what units are on top? Moles. So we have 1 mole of potassium sulfite per every 158 grams. And then finally, if we want to calculate formula units, how many formula units are present in 1 mole of potassium sulfite? What number do we use to count particles? Avogadro's number, which is 6.02 times 10 to the 23rd. Does that make sense? You only use Avogadro's number when you're dealing with particles. So then, let's now punch this into our calculator and let's see what we get. So we have 20.3 divided by 158 times 6.02 EE23, and that in turn gives us 7.73 times 10 to the 22nd formula units of potassium sulfite. Don't worry if there's some drift. Don't worry if there's some drift in the last digit. Your answer is perfectly acceptable. It's likely due to the fact that I rounded my molar mass. On an exam, I'd like you to use the longhand molar masses. I'm only just rounding in this demonstration to save space. Any questions on these calculations involving two-step conversions from grams to particles? Okay, if we don't have any other questions, let's now move on to really start to get to something interesting here. So the chemical formula is really a powerful tool that provides a relationship between the moles of a molecule and the moles of atoms of an element in that molecule. So it's a relationship between the molecule and the number of atoms of each element in that molecule. Additionally, the formula provides a relationship between the number of molecules and the number of atoms of an element in those molecules. So we call this fundamental ratio the formula ratio. It's the ratio of the moles of an element to the moles of a compound. The other way that the formula ratio, another form of the formula ratio, is the ratio of moles of one element in a compound to the moles of another element in the compound. So let's showcase how we can use the formula ratio, and let's take a look at N2O5. Now, let's start with just counting here. How many nitrogen atoms do we have in a molecule? 2. So we have 2 nitrogen atoms per every 1 N2O5 molecule. Right? So we have a relationship between the atoms, number of atoms of an element, and the number of molecules. We can write this atom to molecule ratio as a mole ratio. So we have 2 moles of nitrogen per every 1 mole of N2O5. Let's now develop a relationship for oxygen. How many moles of oxygen do we have? 5. So we also know that we have 5 moles of oxygen per every 1 mole of N2O5. Now we're going to get a little bit more sophisticated here. Do we know the relationship between the moles of nitrogen and the moles of oxygen? Can we take the ratio of those two? So let's showcase that. Let's showcase that. So I'm going to switch pen colors, and my question to all of you is, how many moles of nitrogen do we have? How many nitrogens do we see? 2. So we have 2 moles of nitrogen for every how many moles of oxygen? How many moles of oxygen do we see? 5. Now, of course, we can also flip this conversion factor and say we have 5 moles of oxygen for every 2 moles of nitrogen. So from the chemical formula, we've been able to extract at least 5 or 6 different conversion factors for both a mole to mole and an atom to molecule ratio. Does that make sense? Yeah. Now, let's use this mole to mole ratio. Let's use our formula ratio in calculations. So how many moles of nitrogen are in 13.5 moles of N2O5? Okay, so I know I'm going from moles of N2O5 to moles of nitrogen. And for mole to mole conversions, when you're going from moles of a compound to moles of an element, you're going to use your formula ratio. So given that I have 13.5 moles of N2O5, my question to all of you is, if we're going from moles of N2O5 to moles of nitrogen, what goes on top? Moles of nitrogen, exactly. And how many moles of nitrogen do we have in 1 mole of N2O5? 2. And this we don't even need a calculator for. That gives us 27.0 moles of nitrogen. Now, this really highlights an important subtlety that I want you to keep in mind. Is this mole to mole ratio? How many sig figs are in that mole to mole ratio? So if it's a ratio from numbers obtained by counting, such as counting atoms in a formula, this number is exact. So this mole to mole ratio will never constrain the sig figs you can report. Does that make sense? Okay. Now, what I want you now to do is to apply this idea of mole to mole ratios, and I want you to tell me the moles of oxygen in 13.5 moles of N2O5. So take about a minute and a half to work through that, and then we'll discuss as a group. Everything going okay? Yep. Yep, that's good. Yep, that's good. Everything going okay? Yep, looks good. As I see a lot of reasonable responses, we're gonna huddle together and now discuss this problem. So just like previously, we're going from moles of N2O5, this time to moles of oxygen. We know that we have 13.5 moles of N2O5. And my question to all of you, if we're going to moles of oxygen, what units need to be on top? Moles of oxygen, exactly. So how many moles of oxygen do we have in 1 mole of N2O5? 5, yep. So that in turn gives us 67.5 moles of oxygen. Everyone's okay with doing that on their calculator on their own, right? Okay. Okay, so now that we've introduced this idea, let's now start to combine this formula ratio to generate more complicated unit conversion strings. So, just to make this very explicit, the formula ratio also provides a relationship between the atoms of each element. So, for example, I can ask you how many moles of nitrogen are in a sample of N2O5 containing 4 moles of oxygen. So the way to handle this problem, you can do it in a 1-step or 2-step method. So we're going from moles of oxygen to moles of nitrogen. Now, given that we start with 4.0 moles of oxygen, my question to all of you is, what units are going to go on top in our conversion factor? Nitrogen, yep. So let's plug that in. So now we have to fill in the blanks here. We have how many moles of nitrogen per how many moles of oxygen? What's our mole to mole ratio? 2 to 5. Okay, and now we punch that into our calculator. 4 times 2 over 5, and that in turn gives us 1.6 moles of nitrogen. And notice we're describing all of our elements in their monoatomic form because we're talking about composition. Does that make sense to everyone? We're talking about the masses of each element. So they're atoms and amounts of each element in our formula. That's why it's written as the atomic form instead of N2, the molecular form. Okay, let's get some more practice on using this mole to mole ratio. So I want you all to quickly tell me how many moles of oxygen are in a sample of N2O5 containing 3 moles of nitrogen. So work on that for a few moments and then we'll come together to discuss. Everything going okay? Everything going okay? Which pages do you please? Just add on to this last portion. It's something I added to this page. Yeah. Everything going on? Yep, looks good.
Yeah. Yes, that's it.
So what are we starting with moles of oxygen or nitrogen?
Oh, oxygen.
Oh, isn't the problem? We're starting with nitrogen. Yep, so your conversion is just should be flipped.
Okay.
So I see a lot of reasonable solutions. Everyone's getting a little bit faster at that. That's good. That's good. So let's now just do a quick unit analysis. We are starting with the moles of nitrogen, and we want to report the moles of what? Yeah, so we're starting with the moles of nitrogen, and we want to report the moles of oxygen. So then, given that we have 3.0 moles of nitrogen, and we're going to moles of oxygen, my question to all of you is, what units go on top? Moles of oxygen. So how many moles of oxygen are present per how many moles of nitrogen in N2O5? How many moles of oxygen do we have? 5. And how many moles of nitrogen do we have? 2. So that in turn gives us 7.5 moles of oxygen when you punch that into your calculator. Does everyone understand how the formula ratio functions? Now what we're going to do is we're going to take all of these conversion factors and combine them together to make and deal with higher order problems. So, to showcase an example of a higher order multi-step problem, I've indicated a color-coded problem-solving scheme. So if we want to go from grams to moles, and just to refresh everyone on how this color coding system works, if you see a blue arrow, you're going to divide. If you see a red arrow, you're going to multiply. That way, at the bare minimum, even if you're having trouble with unit analysis, you at least have a heuristic to approach these problems from. So let's utilize this problem-solving diagram to solve the following. We're asked to determine the moles of chlorine in 16.0 grams of carbon tetrachloride. Okay? So we are starting off with grams of carbon tetrachloride, and we want to report the moles of chlorine atoms. What is our intermediate stepping stone? Moles of what? Carbon tetrachloride, right? So in general, the role of our formula ratio is to relate the moles of our molecule to the moles of atoms found in our molecule. Okay, so now with this established, what we're going to do is we're going to highlight what conversion factors we're going to be using. So looking at our problem-solving scheme, if we want to go from grams to moles, what do we do? Yep, and do we multiply or divide by our molar mass? Divide, yep. So notice the arrow going to the right is blue, so we're going to divide by our molar mass. Now, if we're going from moles of carbon tetrachloride to moles of chlorine, we are going to need to use our formula ratio. Okay, and the formula ratio isn't as cut and dry since there are many ways of writing the formula ratio. So for that, we're going to have to use straightforward unit analysis. Now, given that we need to figure out our molar mass, let's quickly calculate the molar mass of carbon tetrachloride. So reaching into our periodic table, what's the mass of carbon? 12. Okay. Now, what is the mass of chlorine? Going to our periodic table, let's just look and remind ourselves where we're getting all these numbers from. So we zoom in on chloride. What is chlorine's atomic mass? 35.5 roughly. So let's go back to our notes. So we have 35.5 grams, and we have how many chlorine atoms? 4. So that in turn gives us a molar mass of 154 grams per 1 mole of CCl4, or carbon tetrachloride. We now have all the information we need to complete this unit conversion. So let's now execute on that. So we have 16.0 grams of carbon tetrachloride. And my question to all of you is, what units will go on top? If we're going to moles of carbon tetrachloride, what's going to go on top? Moles. And more specifically, moles of carbon tetrachloride. So in 1 mole of carbon tetrachloride, we have how many grams? How many grams do we have? What's our molar mass? 154, exactly. Now, and this is where things get a little bit interesting. If we're going from moles of carbon tetrachloride to moles of chlorine, what goes on top? Moles of chlorine. So how many moles of chlorine do we have in 1 mole of carbon tetrachloride? How many chlorines do we see? 4. So we put a 4 for our moles of chlorine. Okay, we're now ready to punch this number into our calculator. So let's do just that. So we have 16 divided by 154 times 4. And that should give us 0.415 that we round to 0.416 moles of just atomic chlorine. Does it make sense? Does our number reported match the sig figs in our input? Yeah. 3 sig figs in, 3 sig figs out. So what I want us now to consider is another form of this problem. So another form of this problem is going to ask you what mass of a molecule contains a certain number of moles of carbon. Now, this problem is requiring the same unit conversion that we did in its first example, except in reverse. So let's showcase that. So what are we given? What are we given initially in this problem? Yeah, the moles of carbon. And in the end, we're asked to report the grams of acetylene, C2H2. My question to all of you is, what is our intermediate unit? To get the grams of acetylene, what do we need to know? Moles. The moles of acetylene that we get from the mole ratio. Now, to get into the details on how we're going to go from moles of carbon to moles of acetylene, one of your classmates astutely pointed out we're going to need the formula ratio. Now, if we want to go from moles of acetylene to grams of acetylene, what conversion factor will we need? Molar mass, exactly. And if we look at our topmost solution map, if we wanted to go from if we want to go from moles to grams, what do we do with our molar mass? Do we multiply or divide? Multiply. Okay, so we're going to multiply by our molar mass. Okay, let me just zoom in to give us a ample space for this next problem. Now that we have all of this information in hand, let's do a quick molar mass calculation. So what is the mass of carbon? 12. Okay, so we're going to take 12.0 grams times 2, because we have how many carbon atoms? 2. What is the mass of hydrogen? 1. Yeah, so we'll write this as 1.0 grams. And then how many hydrogen atoms do we have? 2. So that in turn gives us a molar mass. Our molar mass is equal to 26.0 grams in 1 mole of C2H2. Okay, perfect. We now have all the information we need to complete this problem. So let's just finish this problem off. So if we have 4.0 moles of carbon and we're going to moles of C2H2, what units need to be on top? Moles of C2H2, exactly. So in 1 mole of C2H2, we have how many moles of carbon? How many carbons do you see? 2. Now, to finish off this problem, if we're going from moles of acetylene, which is C2H2, to grams, what units need to go on top? Grams. So we have 26.0 grams per every 1 mole of C2H2, for every 1 mole of acetylene. Now, all you have to do is punch it into your calculator, and you're good to go. So let's do just that. So we have 4 divided by 2 times 26. And that in turn gives us a mass of 52 grams of acetylene, C2H2. Does that make sense to everyone? So what we're now going to do is we're going to have you work on a few of these examples in groups. So what I want you to be able to answer is I want you to tell me what mass of nitrogen triiodide contains 5 grams of iodine and how many moles of sulfur are in 32 grams of hydrogen sulfide. Now, the only thing that's new in these problems is that you are required to figure out what from the name. The formula. So this is a nomenclature game. So to help everyone out on this process, what we're going to do is to ensure that we're really focusing on the mole-to-mole conversion, we're going to do the nomenclature part together. But I'm going to need your input here. So nitrogen triiodide. Would someone like to volunteer a formula for that? Oh, yes. So that would be Ni3. Would someone like to volunteer a formula for hydrogen sulfide? Jacqueline, I saw you had your hand up. It was H2S, exactly right. So hydrogen sulfide, this is the gaseous form of an acid, and it's written as H2S. To balance out the sulfur's 2- charge, H+, we cross our charges, and that gives us a total of 2 hydrogens. So the point of these problems is to really showcase, if you don't know your nomenclature, it's going to be very hard to answer these questions. Okay, so I want you now to work on these problems with these formulas in mind, and we'll come together as a group to discuss in a few minutes. Everything going okay? Everything going okay? Okay. Everything going okay? Okay. Everything going okay? Very, very close. We need to start from the grams by. Yep.
Oh, so I just switched the order?
Oh, so instead of starting with moles, you're going to go through grams of iodine to moles. Here's what I'm saying. Everything going okay? And then we're given not the grams of nitrogen triiodide, but the grams of iodine to start with. Everything going okay? So then the grams, it's grams of iodine. So you're gonna have to do one more step in the conversion. Yeah. Yes. Yep. You have to go to moles. Okay. So in between these two. Everything going okay?
I have 5 grams of yeah. So do we go from here to gold?
Yeah.
Okay.
The first one, I'm asking for the mass of nitrogen triiodide. Yep. But the second one, may I check? Yes, the only thing they'll need to go from grams of iodine to moles. But otherwise, it's very good. So to help everyone out on this problem, and to help everyone showcase the subtlety of this problem, so I'm asking what mass of nitrogen triiodide contains 5 grams of iodine? So we're starting off with the grams of iodine, and in the end, we want the grams of nitrogen triiodide. Now, one thing I really want to impress on all of you is this idea of making a solution map. You can tackle any problem if you've organized your thoughts in a way that highlights what units I'm going to go to in each step of my conversion. So we're going to need to have a few bridging units here. So how do we relate an element to a compound? How do we relate an element to a compound? What ratio? The ratio of what? Two quantities. What do you call the ratio that relates an element to a compound? The formula ratio, right? And the formula ratio, is it a mass ratio or a mole ratio? The formula ratio? It's a mole ratio, right? So then, if we want to get the grams of nitrogen triiodide, what will we need to start from? How do we get grams? Where do we get grams from? Moles, right? So we know that we're going to need to figure out the moles of nitrogen triiodide. Does that make sense? Now, how can we get the moles of nitrogen triiodide? Can we get it from our formula ratio? Yes. And that would require us to know the moles of what? What are we given? Iodine. So we need the moles of iodine. Okay. So the only thing that's new compared to what we've done previously is this conversion here. We get our moles of an element from the mass of that element. Once we have the moles of iodine, we can use our formula ratio to get the moles of our nitrogen triiodide, and the mole to mass conversion, we know how to do that using our molar mass. So just to highlight the conversion factors in each step. So for step number 1, we're going to divide by the molar mass of iodine. For step 2, we're going to use our formula ratio. And then finally, for step 3, when we want to go from the moles of nitrogen triiodide to the mass, what do we multiply by? Molar mass. So we're going to multiply by the molar mass of nitrogen triiodide. Does that make sense to everyone? So now that we have that established, let's do a quick sidebar calculation for the molar mass of nitrogen triiodide. So what's the mass of nitrogen starting off? 14. And what is the mass of iodine about? Yep, about 127. And how many iodine atoms do we have in our compound? 3. So then that gives us a molar mass, and I'm going to break out the calculator for that. 127 times 3 plus 14 gives us a molar mass of 395. So let's plug that in. This is 395 grams per mole of nitrogen triiodide. Okay, we now have all the information we need to begin solving this problem and finish solving this problem. So starting off with our 5.0 grams of iodine. Our first order of business, we're going from grams of iodine to what? Moles. And in 1 mole of iodine, monoatomic, we have how many grams? What is iodine's atomic mass? Yep, which is about 127. Okay, next, we're going to use our formula ratio. We're going to use our formula ratio. And if we're going from moles of iodine to moles of nitrogen triiodide, what units will go on top? What units will go on top? We're going from moles of iodine to moles of nitrogen triiodide. Nitrogen triiodide, exactly. So we have 1 mole of nitrogen triiodide per how many moles of iodine? How many iodine symbols do we see? 3, exactly. Finally, if we're going from moles of nitrogen triiodide to grams, we're going to multiply by our molar mass, which is 395 grams per every 1 mole of nitrogen triiodide. And if we punch this into our calculator, we have 5 divided by 127 divided by 3 times 395. And that gives us a final output of approximately 5.2 grams. Why am I rounding this to 5.2? How many sig figs does our input have? 2. So then, let's write down our final answer. We would expect to have a mass of 5.2 grams of nitrogen triiodide. So, with that established, what I would like everyone to do is to take a little bit of additional time, continue working on the second example, and then we'll discuss in approximately 2 minutes. Any questions? Everything going okay? Yep, that's good. Any questions? Yep, looks good. Yep, looks good. Oh, I'm asking for the moles of sulfur. Yep. Yep. Oh, we're given the mass of hydrogen sulfide, so we divide by the molar mass of hydrogen sulfide. Does that make sense? Everything going okay?
Is the solution good?
We don't need to go to grams of sulfur because it's not required in any of our solutions. Okay. You can go directly from moles of compound to moles of an element using the formula ratio. Okay. Everything going okay? Yeah. Okay. So I saw a lot of reasonable answers. I'm very impressed how quickly everyone was able to tackle this problem. Let's now talk through this solution together, and let's talk about what we know and what we are trying to figure out. So we are given the grams of hydrogen sulfide, H2S. And what are we looking to calculate? What are we trying to report? Moles. More specifically, the moles of sulfur. This is why labels are important, because they affect what conversion factors you use. So how are we going to get the moles of sulfur? Where can we calculate moles from? We can calculate the moles of an element if we know the moles of so if we're given the mass of an element, yes, we can calculate moles that way. But in this case, we're given the mass of H2S. So what's a convenient bridge between the mass of H2S and the moles of sulfur? the moles of H2S, exactly. A common way you calculate the moles of an element is from the moles of a compound. Now, with this established, we're now ready to fill in our solution map with a little bit more detail. To go from grams of H2S to moles of H2S, we're going to divide by our molar mass. And then to go from moles of H2S to moles of sulfur, we're going to use our formula ratio. So, with the solution map partially established, we are now ready to execute on this problem. Is there something that I forgot? Is there something that we need to figure out? Do we have all the numbers just ready to go? For the most part, but let's show how to calculate this molar mass, just to make sure we're all on the same page on that. So looking at our molar mass, we know sulfur has a mass of 32 grams, hydrogen has a mass of 1.0 grams, and how many hydrogen atoms do we have? 2. That in turn gives us a molecular weight or molar mass of 34.0 grams for every 1 mole of H2S. We're now ready to execute on this conversion. So we have 32.0 grams of H2S. If we're going from grams to moles, what units need to be on top? Moles. So then let's fill in our conversion factor ratio. In 1 mole of H2S, we know that there are 34.0 grams. Additionally, let's now fill in our formula ratio. If we're going from moles of H2S to moles of sulfur, what units need to be on top? Moles of sulfur. So how many moles of sulfur are present per mole of H2S? What is our mole to mole ratio? 1 to 1, exactly right. So now all we have to do to complete this problem is punch it into our calculator. So we have 32 divided by 34. That gives us a grand total of 0.941 moles of sulfur. Does that make sense? Okay, now let's apply this idea to more complicated. We're slowly adding complexity to our unit conversions. So, in this case now, we're asked to do a 3-step conversion, and these will be the last examples that we'll address today. So, in this problem, we're asked how many potassium ions are in 3.0 grams of potassium phosphide. So to highlight our solution map here, we are given the grams of potassium phosphide. And what are we being asked for in this problem? What are we asked to report? The number of ions, so particles, so K plus ions, which you can think of similar to the idea of K plus atoms. Now, where do we calculate atoms from? Avogadro's number, and what units? What units do we start from? Where do we get, what units do we get atoms from? Yeah, 6 point, that's Avogadro's number, but it allows us to get atoms from what starting point? From moles. Yeah, exactly right. So we're gonna need the moles of potassium plus. Now, where do we get the moles of an element from? You can get it from the molecular weight if you know the mass of the element. That's perfectly fine. But given that we're starting from the mass of potassium phosphide, what is the bridge? How do we get moles of an element from the mass of a compound? You need the moles of potassium phosphide. Exactly. So we're going to need the moles of potassium phosphide. You get moles of an element typically from the moles of a compound using the formula ratio. Now, to fill in the blanks here on how we're actually going to execute this conversion, if we want to go from grams to moles, we're going to divide by our molar mass. When we do a mole to mole conversion, we're going to use our formula ratio. And finally, if we want to go from moles of atoms to just atoms, if we want to go from moles to particles, what do we multiply by? Avogadro's number. So we're going to multiply by Avogadro's number. So with that all established, we just need one more piece of information. And let's figure out the molar mass of potassium phosphide. Okay, so what's the mass of potassium, roughly? 39, yep. So 39.1 grams. And how many potassium atoms do we have? 3. Would someone like to volunteer? What's the mass of phosphorus from our periodic table? Let's see. Yep, 30.97. Yep. We'll just round it to 31.0 to save space. And we have one phosphorus, so we're good to go. Let's calculate that. 39.1 times 3 plus 31. That gives us a molar mass of 148.3 gram per mole of potassium phosphide. Okay, we now have everything we need to complete this problem. So let's execute on that. We have 3.0 grams of potassium phosphide. If we're going from grams to moles, what units need to be on top? Moles. So we have 1 mole of potassium phosphide per every 148.3 grams. The next question, we're going to need to fill in our formula ratio. And if we're going from moles of potassium phosphide to moles of potassium ion, what units are on top? Moles of potassium ion. So how many moles of potassium ion are present in 1 mole of potassium phosphide? 3, yep. Finally, if we're going from moles of an atomic species to particles, what conversion factor do we use? How many total ions are present in a mole? Yep, Avogadro's number, 6.02 times 10 to the 23rd K plus ions in 1 mole of potassium plus. Okay, so with that established, all we have to do now is enter that into our calculator. So we have 3.0 divided by 148.3 times 3 times 6.02 times 10 to the 23rd. And you should get at the end of this lengthy calculation 3.7 times 10 to the 22nd. Does that make sense to everyone? We'll start off next class session with you performing an example calculation in the second part of the notes. But that's all I have for today.